So people on YouTube, sorry to put the cut in the middle of a problem. I messed up. So think about the sign of the work done by the spring. Is it doing positive or negative work? Um, Try to get your answers to me in 20 or 30 seconds. There's still a lot of people who haven't answered yet. All right, so most people have said B, which is correct. Um, so you know the spring is doing positive work. Since the force is in the direction of motion. Now, there are two ways to figure out the work done by the spring. Um, I'm going to kind of briefly talk through both of them. The simple way, the easiest thing, is to say that what the spring is doing here is that it converts its elastic potential energy into kinetic energy. And you know that the formula for elastic potential energy is 1/2 k times the stretch or compression distance squared. So if this elastic potential energy is being converted into kinetic energy, that's called positive work, right? Work is change in kinetic energy. So since work is the change in kinetic energy, the elastic work is just 1/2 kd squared. So that's one way to do it. But how did we know that? How did we know that this was the formula for the elastic potential energy? So whenever I ask for a new page, I have to scroll back down. It's a glitch in this program. So doing this out in full, if I want to just use the definition of work, I have to actually do an integral here since the force is not constant. And so I'm going to write minus d here because it's compressed a distance d and it's going to neutral. So here, you will never need to do this integral. I'm just showing you where the potential energy formula comes from, because I think sometimes we neglect to do that. So here, how do we know force is not constant? So remember that the elastic force is minus k times the stretch or compression distance. So as like when you push the spring in all the way, it's exerting a very large force. And as the spring releases, its force goes down and down and down. So if we graph this, right, so here's some coordinate axes. If we graph this, where we put on this axis, and then on this axis we put force, then the graph for the spring force looks like this. So if you compress the spring, it tries to make itself longer. If you extend the spring, it tries to make itself shorter. And at the equilibrium point, the force is 0. But it's changing, is the point. So I know the elastic force is k delta x, so let's put that in. Minus kx dx. This is going to be, now I can reverse the so is k the average force exerted by the spring? No, what k is, let me erase this. So k is called the spring constant. It's measured in newtons per meter. And what it tells you is how many newtons of restoring force does a spring produce per meter of stretch or compression. So that's what a spring constant means. Let me, I'm going to grab one more new page here, just so I can finish this. So the work done, we saw that it was the integral of force dx, which is the integral of kx dx. This gives you 1/2 kx squared, in short. So what we did is we, the approach to doing this integral is we figured out once the work done by a spring. And now we can say, the elastic potential energy is just 1/2 k delta x squared. We can remember this and never need to do this integral again. Samantha, why did I plug in positive kx for this integral? Because I don't want to spend a lot of time belaboring this point. It turns out that all of those minus signs cancel and you wind up getting a positive work in the end. I didn't flog those minus signs because really we're not going to be doing this integral on the fly, and I wanted to save time. I can do the whole thing out and like track all the minus signs and flip the limits here. You know, and show you where all those minus signs go later if you want. But for our purposes, I wanted to just keep going. James, when you say it's different for every problem, what do you mean? Oh, the spring constant. I see you're responding to Deanna. The value for the spring constant is different for every spring. So the spring constant might be very, very large if you're dealing with the super stiff springs that are, say, the shock absorbers on a pickup truck. But if you're dealing with the little spring in a ballpoint pen, then it's going to be very small. So let's move on here. So we've talked about the work done by the spring, and we've seen that it does that much work. Tell me about the work done by gravity. I need to push the button here to let you all answer again. So tell me about the work done by gravity. I'll take maybe 30 seconds for your answers here. So great question. Derek asks, at the beginning or during their ride? So that's a really, really good question. Remember that work is associated with a motion. So we're thinking about the motion from point A to point B here as we travel along that path. Yeah, right, Martin. It's not terribly illuminating. We know that the work done by the spring is positive, just because it's pushing a thing in the direction it's going. All right, take 15 more seconds to tell me about the work done by gravity. Okay, the overwhelming answer was C. Unfortunately, I pushed the button that doesn't show you the answers. My bad. I'm still learning how to use this tool. Kevin, did you have a question? You hit the raise hand thing, but trying to see if you still have your hand up is being very laggy. I guess not. No worries. People are saying that the work done by gravity is C, which is correct. Remember, the work done by some force is the size of that force dot product with the displacement. This means the force times, write it this way, times the component of that force parallel to displacement. So for gravity, this is just going to be mg times the displacement downward. And if you imagine this as a right triangle in our problem, then this distance here, the displacement in the y direction, is just L sine theta. Where the L sine theta here again comes from that. Everyone with me so far? All right, now let's think about the next one. Tell me about the work done by the normal force. How did you know you wanted the change in y rather than x? Because to calculate the work done, we want the the force times the component of that force. Actually, let me erase this and write one more thing. Because I wrote one thing and then I used the other method. Or you can calculate work done as oh, I realized what I messed up. I'm sorry, I was going too fast and I had a brain fart. What I meant to say was force times the component of displacement parallel to that force. That's what I meant to say. I'm sorry, I didn't have enough breakfast and I'm not thinking clearly. So, since here force is downward, so the work done by gravity is the force of gravity times the distance moved downward equals mg times L sine theta, which is mg times delta y as Griffin has pointed out. Brianna asks, why is it L sine theta and not just sine theta? Because what I want is the distance moved downward. So if this side of the right triangle is L, then this one here is L sine theta. I'm going to kind of not do the polling for these next few, just in the interests of time. I want to make sure that we get to the new topic for today, which is power. The work done by the normal force is 0. Since the normal force is perpendicular to the displacement. That's often the case, not always. The last one is the work done by friction. And here, I will do a poll for this one. So tell me about the work done by friction. We'll take maybe 60 seconds on this. So I see some people are accidentally misclicking the raise hand button. If you accidentally raise your hand, just lower it again. I don't know why they put those buttons next to each other. Yes, Martin, there was a typo on the slides originally. What you see on your screen right now is correct. There should be an L here. Okay, take 10 more seconds and then we'll see what everybody says. Okay, the majority answer here is B, which is correct. So how do we know that? So here, the work done by friction is going to be the force of friction times the displacement parallel to that force. Now, the most popular incorrect answer was C. Let's talk about why C is not correct. So the force of friction, wrong tool. The force of friction goes this way. The displacement is that way. In this case, though, rather than only wanting the vertical component of the displacement, we want the component of the displacement like up and down the ramp. So this is the force of friction times the displacement along the slope, which in this case is the force of friction times minus L, not L sine theta. Because in this case, the force, rather than just being up and down, prompting us to look at only the vertical component of displacement, the force here is up the ramp. So we have to look at the entire displacement here. The force of friction then is mu times the normal force, which is going to be mu mg cosine theta times minus L. Notice that this whole thing here is the normal force that you get from doing your Unit 2 free body diagram stuff. Any questions before I move on? Okay, so now we have figured out the work done by all of these forces, and now what I want to do, why is the work done by the normal force 0? It's because the normal force is perpendicular to the motion. So, you know how like for the work done by gravity, I had to figure out the displacement in the direction of the force of gravity? Well, here, the normal force is perpendicular to the slope, the motion is parallel to the slope, and the component of the motion in the direction of the force is 0. Dante asks, if we tilt the axis relative to L, would it be sine theta? No. So an interesting thing about work is that it's a scalar. It doesn't depend on your coordinate axis. So yes, if you tilt the axis, then the geometry you have to think about in computing the component of one thing in the direction of another thing may become more complicated, but you'll always get the same answer. One thing that you can remember is that the work done by a force is the force times the displacement times the cosine of the angle between them. And saying cosine of the angle between them, that doesn't depend on your coordinate axes, right? So you're always going to get the same value of the work regardless of your coordinate axes. So here's what I'd like to do, and this is kind of a throwback to the question that that Jazz asked in the beginning of class, which is how do we think about different kinds of energy and potential energy in the context of the work energy theorem. So what I'd like to do now that we've got this whole problem set up, is I'd like to do this problem twice. Once with the work energy theorem, the plane work energy theorem, and once with conservation of energy. Oh, wrong tool. And I'm going to put a cut in the YouTube video here.